Today we'll discuss those topics. Linear transformations, and in particular isomorphism, some notions like nullity, rank. Those are the topics. What is linear transformation? We have discussed earlier that a linear transformation given to vector space V to W. Now we can define a function from V to W. Suppose T be the function, capital T. Now we'll say T to be a linear transformation, we need to satisfy those properties. That is it T preserve addition and multiplication, scalar multiplication. What is the meaning of this? This means T of two element V plus W. This is same as first apply T and then add. And similarly, if we multiply V with some scalar C, then apply T, it will be same as first apply T and then multiply it with C. If those two properties hold, then we'll call it a linear transformation. Okay. So what are the example of this? So we can write those two property in a single way, that is T of C1 V1 plus C2 V2 is same as C1 times T V1 plus C2 times T V2. Okay, and there is another way to write those two properties in a single format, which is T of C1V or CV, here one constant, CV plus W or V1 V2. Let's this is same as C times TV1 plus TV2. Okay, then we'll call it a linear transformation. Here note that all Ci belongs to the scalar field F, and all Vi or W, whatever, those comes from the vector space V itself. This is the definition of linear transformations. And we have also noted that T of 0 is 0. That is 0 is invariant under linear transformation. Linear transformation.
Zero vector, right, sir?
Huh?
In the transformed field itself, a vector space itself, zero exists, right, sir?
Yes.
Zero vector, yeah.
Since V and W are both vector spaces, so there is a 0 in V and there is 0 in W also. And those 0 can be different, but there is some 0. Okay. So I am saying that 0, that is this 0 comes from V and this 0 comes from W. Yes, you are right. So those are some beautiful properties of linear transformations, and we have seen some examples. For example, consider this map T of x1, x2
Sir, one question. This just now you explained how t of zero comes from V vector space and zero comes from W. Can you please help me understand this line?
Okay, so for example, consider let us consider a linear transformation. Define T from this R2 to the square matrix 2 by 2 square matrix. How do we define this? Suppose T of x1 comma x2, this is defined by x1 x2, and suppose this is also x1, this is 0. Then let us check if T is linear or not. So you can see that if we add answer, suppose x1 x2, this belongs to R2, and another x1 dash x2 dash, this is also belongs to R2, and suppose C belongs to the scalar field R. Then first add, this is V1 and this is V2. First add CV1 plus V2, then clearly you can see that it is component wise addition, so it will be C1x1 plus x1 dash, and similarly C2x, sorry, there is only single C.
So C1 X1 dash, sir.
Uh, there is only single C, so it is C.
Oh, yes, sir. The first component should be added, right?
Yes, CX1, CX2, and X1 dash, X2 dash. Then addition is CX1 plus X1 dash, CX2 plus X2 dash. Okay. And if you now apply T on this CV1 plus V2, then by the rule, that is T apply on this thing, T apply on CX1 plus X1 dash, CX2 plus X2 dash. By the rule, this rule, we have, this is same as first entry will be CX1 plus X1 dash, and this is also same. This is CX2 plus X2 dash, and this is 0 by the rule start. And you can split it in this way. You can split it as CX1 x1, and here is x2 0 plus x1 dash x1 dash 0 x2 dash. And now note that this c times this is actually transformation of x1 x2. By definition of t, this is t of x1 x2 multiplied with c, and this is actually t of x1 dash x2 dash.
Mm-hmm.
So now you can say that T is linear because T preserved the scalar multiplication and addition structure. Okay, so you can claim T is actually linear transformation. T is a linear.
Well, actually, I was looking for clarification on the zero.
Yes. Now, if you use this rule, what is 0 in R2? 0 in R2 is, it will be like 0 comma 0. Okay.
Mm-hmm.
And what is 0 in M2 cross 2, 2 by 2 matrices? It is 0 everywhere.
Yeah.
0, 0, 0,
If we
0.
apply T, then you can, by this rule, this is actually 0 0 everywhere.
Okay. So you said that T of zero is from V, and then the output zero is from W.
Yes.
What did you mean by that? I just want to understand it that
Actually,
only.
this 0 comes from 0 in R2, and this 0 comes from 0 in M2 cross 2. Okay.
Oh, okay, okay.
This
You're
is
saying
actually notation. In vector space, 0 is a notation which can be anything. It may not be a single 0
okay.
transform real number. It can be a pair, order pair like this, or you have seen in an example that 0 is 1 comma 0, that behaves like 0 in
But sir,
some cases.
one question. We say t of 0 comma 0, we
Yes,
are actually having two vectors in that, right? V1, V2. So
yes.
it is like a matrix only, correct?
Oh, which thing?
The t 0 comma 0,
Yes,
the
you can
0,
thought this R2 as matrix 1 by 2 matrix.
yes,
You can thought it as this also.
1 by 2. Okay,
One
okay.
row and two column.
So isn't this individual 0 0 like individual matrices like V1, V2? We had V plus W, right? You had like T of V plus W, correct?
T
So
of,
in the rules,
yes, in the rules.
have T of V plus W is equal to T of V plus T of W.
Yes, this is
So here when we say T 0 comma 0, uh, is that like how is that?
that 0 comma 0. It is not two different thing. It is a single vector.
Oh, okay, okay,
Yes.
okay.
So you cannot
So it
think this 0 and this
is
0 are different.
okay, okay. So this is like the second rule C of V. So this is like V.
Yes,
Okay. And then with the on the right hand side of the equation, that
yes,
zero is an actual matrix.
yes, right.
So what can you please tell what did you mean by that zero is from W?
Because this 0, this
Hmm,
is not the same as 0 comma 0, right? This
correct.
is a different thing.
Yeah, yeah.
Though this is a 0, but this 0 arises from W, the vector space W.
So
This is what.
can you please derive this? I'm not very clear how this two by two this 1 by 2 matrix became 2 by 2.
By this rule, right? If
That
you
would be
put
of helpful.
if you put x1 is 0, x2 is 0, because of this rule, this becomes 0 0, and this is also 0. So now you will get t of the 0 vector. It is 0 everywhere. That is 0 vector in the matrix 2 by 2 matrix.
In the matrix, so the two coordinates are x1 and 0, which is vector, and the other one is x1 and x2, right, sir?
Yes, right. This
How
is
do we actually fix it in that way, sir? Or could we take any other combination of it? Is it
yes.
like
You can take any other
x1 x?
combination, but you need to check that this is also linear. Okay. You can take any other combination like x1 plus x2 here. Okay, and you can check that this is also another linear transformation, not that but a different linear transformation. Swati, is it clear or
Sir, I'm trying to understand still this proof which we have done. No,
yes,
so we are saying that T of x1 comma x2, that is T of V, is
yes,
equal to a matrix which is equivalent to x1 x2 0 x1 x1 x0 x2.
yes.
And can you please quickly tell once again about
Okay,
like
let
how?
us
Yeah,
check it again. And actually, given that t is defined in this way, okay,
yeah.
now we have taken two vector from R2 from the domain.
Okay,
So two vector will look like in this form x1 comma x2, an order pair. Okay.
correct.
So we have taken these two vector and
Mm-hmm.
a scalar c from real
Okay.
number.
Mm-hmm.
Now we have taken that linear combination cv1 plus v2,
Mm-hmm.
which is same as this.
Mm-hmm.
Now we have applied t on this combination, and by the rule we are getting this is nothing but this matrix.
Okay.
And now if you can write it in this way, okay,
Okay. Mm-hmm.
but this is actually same as t times t of x1 x2 by the
Mm-hmm.
same. by same definition, it is actually T of x1, x2, and it is x1 dash, x2 dash.
Mm-hmm.
So that is why,
Matching our first rule, is it?
yes, this is actually the first rule. Those
Okay.
rules which are combined in this form or in this form. Okay.
So since it is matching the rule, this means whatever is given to us is a linear transform.
Yes, it is
Okay.
not only a function, it preserves the linear structure. That is
Okay.
why it is linear transforms.
Okay, fine. Thank you. Yeah.
Okay. So let us see some example which we have seen earlier. For example, if you consider defines R2 to R2 by sending T of x1, x2, we are defining this. It is same as x1 comma 0. Okay. Geometrically, it projects everything. Suppose this is a vector 1 comma 2, it will project onto x-axis. Okay. Then it projects onto x-axis. Okay, and this vector is 1 comma 0. So this is projection on x-axis. If you check those conditions, that is t times cx1, if you check those conditions, t of, so you can take v1 to be x1 comma x2 and v2 to be another thing, suppose y1 comma y2, and c from the real number r. Now if you again check the thing, what is t c v1 plus v2? C v1 plus v2, it is same as cx1 plus y1 and cx2 plus y2. Now by the rules, this is same as, it is actually projection onto x-axis, so second component will become 0. Now you can separate in this way, cx1 comma 0, and this is same as y1 comma 0. But this is same as t of x1 x2 by the rule, right? C times t of x1 x2, and this is t of y1 y2. Therefore, t is a linear transformation. Okay. So you need to check only this property. The t preserve the linear structure. If you take some linear combination and if you apply t, this is same as applying first t, then you take the linear combination of those two things. That is, apply first t and then take linear combination of those two things. Okay, this is the definition. Another example you can easily check. Suppose t is again defined from R2 to R2. The definition is t of x1, x2 is interchanging the tuples x2 comma x1. What is geometric significance? It is actually reflection around this x equal to y, this line. Okay, so a point x comma y, this will go to y comma x. Okay, this will be the reflecting point. So y comma x.
This is a reflection on x is equal to y.
Yes, reflection around x equal to y. So
Okay. Thank you.
again, if you check those property, those will be satisfied. So this t also linear. Okay. Now let us take another example. T x1 x2. This is defined by x1 square, x1 square plus x2. Suppose now t is a map from R2 to R. Is it linear? The answer is no. It is not linear. Linear transformation. Why? So let us check why it is not a linear transformation. If you take some element, suppose take 1 0 and 0 1, those two vectors. This is v1, this is actually v2. Okay. Instead of 1 0, let us take 2 0. Now let c equal to 1. What is cv1 plus v2? cv1 plus v2 means 1 times 2 0 plus 0 1. This is same as 2 comma 1, this pair. Now first, if you apply t of this cv1 plus
2, 1, right?
hmm?
T of 2, 1.
Yes, t of 2 comma 1. This is by definition, this is actually 2 square plus 1, which is 5. But if you apply t here, that is t v1, by definition this is actually 2 square. 2 square means 4, and t v2, this is actually 0 square plus 1, which is 1. Okay, so this will not work. We let us modify it 0 0. Okay.
Sir, one ले लीजिए. Sir, if we change the value of C, then it
Oh,
will.
sorry. I have made some mistake. Uh, Instead of c equal to 2, actually we should take v2 to be 1 0, then it will work. Okay.
सर C का वैल्यू चेंज करेंगे
Yes,
तो
c का वैल्यू चेंज करेंगे तब भी होगा.
हाँ.
But let us try this. Sorry for making mistake. 3 0. Then it is actually 3 square plus 0, which is 9. And tv1 is now 4. tv2 is again 1. Now it is, you can see that this is not c times tv1, because c means 1 times tv1, tv1 means 4, and tv2 means 1. Okay, so 5 is not equal to 9, hence t is not linear. Okay, this is the proof.
What does, excuse me, sir.
Yes.
What does it physically imply, sir? I mean,
Okay,
what does it
physically,
graphically imply, sir?
yes, graphically it will imply that is, you cannot, it is not actually every linear combination. This will give some lines or some plane which passes through the origin. Graphically it will imply that this cannot be a, this transformation is actually, so graphically what, this is not the way I have said. uh, Graphically,
I mean, the second one implies the symmetrical graph, sir.
yes, second one
Which
like,
is taking x1 and x2.
yes, yes.
I can understand and picture it in that way, sir. But what does the
Yes.
third example mean, sir?
For the second one, the graph is not clear. What will be the graphical representation? But you can see that
sir, doesn't it
there
mean
is,
that there is an x1, x2 coordinate like a vector,
yes,
and it gets mapped to a this parabola? So yeah, this
uh, truncated. Yes, parabola, which will be paraboloid-like things. Yes.
so it is just like how does transformation work? Does it mean that x1 and x2, x1 comma x2 vector has been transformed in such a way that it
Uh,
lies on
yes,
a parabola.
yes. What you have said is also a right way to see the graphical meaning of this. Actually, this for this case, it will the graphical. If you project on some plane, the graph will look like this, and you can see that it is not a line. That is, the range is not a linear thing. Okay, here the range is not a linear space. Linear space, by meaning of what is the meaning of linear space? It is a plane. It is not a plane or not a line, not that kind of thing. That is what the problem in this case. But this does not imply
So
that if range is line, this does not imply that it will be linear. For example, consider this: t from r to r, t send x to x square. Though image is the straight line r, whole straight line, but this is not a linear. Why? Because it does not behave well. Okay, t of 2, it is actually 4, but what is the meaning of 2? 2 is 2 times 1. Okay, so this should be same as 2 times t1. But t of 1, by definition, t of 1 is 1 square. So 1 square into 2, which is 2. So you can see that t2 and 2 times t1 are not same. Okay, that is why.
makes sense, sir. C is 2, right, sir?
Hmm, you can
C is
you can
C. The value of C is 2, right, sir?
yes, value of c is 2 here. You can say that t is not stretching equally. That is, t stretches 2 by 2 times. You can see the here the stretch is 2 times, but t stretches 1. 1 goes to 1 square. Okay, so here the stretch is 1 times. T does not stretch equally everything. That is a representation of where is the problem. Is it clear?
Yeah, yes, sir.
Okay, so here this is not a linear transformation. We can say non-linear.
Can linear
Hmm? Yes.
transformation occur between what do you call, like, from lower dimension to higher dimension, sir? Like from R2 to R3, can it be transformed? Then?
Okay, let us give an example from lower to higher dimension, R2, R3. So R2, R2, let us see this. So it will be like a curve. T of x, this is same as x comma 2x. So you can see this is actually a curve on R2. The image is a curve. So this is also linear. Okay. To check linearity, instead of checking in this way, you just check in the you can check in this way also. That is, t of x, you can write it as the matrix form. Okay, it is same as so.
We did it just now, no? That projection on x-axis,
Yes,
that xy went to 0x,
yes.
x0. Yeah.
So here you can see that t time, it is actually, yes, matrix representation is not like this. You can see that the matrix representation will be like this. Okay.
Yes, sir. Taking X outside, factorizing as X, right?
Yes, yes. You can thought this actually coordinate are x, and here the coordinate will be x comma 2x.
So,
That is
sir,
what.
this coordinate will be like x comma 0, right?
Yeah. So you can see that if you write it as w, then t of v, t of this v, it is same as a times v. Okay, where a is same as, where a is the matrix 1 2. And we have seen that if matrix multiplication, this is actually linear. Okay, why linear? Why matrix multiplication with a vector linear? Because T behaved well with matrix multiplication. So let us take CV plus CV1 plus another vector V2. And this is same as A times, by definition, A times CV1 plus V2. And you can write it as C times AB1 plus V2. This is nothing but C times TB1 plus V2. Okay. Sorry, here it is A. Therefore, matrix multiplication is a linear transformation. Multiplication is linear. Here also you can write the transformation, this transformation. You can write it as the here the coordinate are like x1, x2, and here it goes to x2, x1. Okay. You can see this is nothing but 1, sorry, 0, 1, 1, 0, x1, x2. So note that here TV is same as multiplication by this matrix 0, 1, 1, 0. Okay. So any matrix multiplication is a linear transformation.
सर ये लास्ट वाला पार्ट एक बार प्लीज देखने दीजिए क्लियरली हो. So it's an identity matrix which is multiplied by the coordinates.
Not identity, but it
Sorry,
is
हाँ.
it is changing first two column.
Elementary matrix, right, sir?
Elementary, yes. It is changing first two column.
Okay, so when we multiply an elementary matrix which is a scalar,
Yes.
with the coordinate, it
Yes.
will give the same coordinates, right?
No, it is interchanging first and
Correct. Yes.
second row.
Yes.
Yes.
So you are saying, like, what are we trying to say here? And
I am trying to say that this is transformation by matrix multiplication. Okay.
yeah.
And we have checked that matrix multiplication is linear transformation.
Okay. Okay.
So instead of checking T is linear or not, we can just say from here directly. Since T is matrix multiplication, T will be a linear transformation.
So because we can write in matrix form, it's a linear
Yes.
transformation.
You can
right,
write
sir?
T is same. What T is doing? T is doing as same as multiplying with some matrix. Okay. That is what I am trying to say.
Okay. Okay. So it is like when we say a matrix, like elementary matrix, it's a scalar equivalent to scalar, right?
No, elementary matrix may not be a scalar. It is not always scalar multiplication of some row.
Okay. Okay, so I'm missing something here, sir. Like, because we are able to transform one vector to another vector by matrix multiplication.
It will be linear.
So, is this something I'm missing? Something like what I'm not able to understand. Is this a rule? Like, if we are able to multiply?
Because here I have given the proof, right? So I have said that if T is A times V, where A is some matrix, you
Yeah.
can check the property. T preserve the scalar, T preserve the linear structure, because T of CV1 plus V2 is same as C times TV1 plus V2.
TV2.
That is
Okay.
why matrix multiplication is linear.
Okay. Okay. Okay.
Okay. So let us check another example. 7. Here given a linear transformation R3 to R2. Okay. The transformation rule is given by x1, x2, x3. maps to x1 minus x2 plus 2x3, 2x1 plus x2 minus x1, minus x3, and minus x1 minus 2x2 plus 2x3. So is it linear or not? What will be the answer? Question, is it?
Excuse me, sir.
Yes.
T
Hello.
should have only two coordinates, right, sir? Because it goes from 3 to 2.
So
Yeah,
it
it
is
goes
R3.
from
Yes.
three dimension to two dimension. It has to have two
Yes, yes.
coordinates, right, sir?
So the question is given from R3 to R3. I have written a wrong thing here. Okay. The print is not visible clearly. That is one. So is it a linear transformation or not? So here also you can write answer yes, T is linear. How can you check that? So let us see some. So the coordinate of x1, x2, x3, this is same as x1, x2, x3. Okay. And under T, this goes to this thing. x1 minus 2 minus x2 plus 2x3, 2x1 plus x2 minus x3 minus x1 minus 2x2 plus 2x3. Actually, this is same as some matrix multiplied with x1, x2, x3. Okay. So what will be that matrix? This is, you can see that this will be 1 minus 1, 2. The second row should be 2, 1, minus 1. And the third row will be minus 1, minus 1.
Minus 1, minus 2, 2.
Okay. So you can see that T of T transform by matrix multiplication. Okay. Where
Sir, आपने ये coefficients, like how did you find them so quickly?
yes, because you can see that here the coefficient is 1, here minus 1, here 2. So first
Okay.
will be 1, minus 1, 2. And
Okay.
for the second.
I got it. Yeah, thank you.
From here you can conclude T is a linear transformation. So let us consider another example. Okay. Suppose T is acted by derivative. So suppose consider the polynomial space P3. P3 denotes polynomial. Instead of P3, let us consider P2. Polynomial of degree less equal to 3. 3. So P3. And consider the derivative map D from P3 to P2. Derivative always reduces the degree. How then the question is D linear? D means derivative. What will be your answer? Let us check. Sorry for this. So you can see that what will be any arbitrary polynomial? It will look like
Ax cube plus bx square plus
yes.
cx plus d is equal to 0, sir.
So a0 plus a1x plus a2x square plus a3x cube. This will be any polynomial from P3, this space. So let us apply D on this thing. Okay. Then what will be?
A1 plus 2A2x
Yes, it will be a1
plus
plus 2a2x
3A3x squared, sir.
3a3 x squared by the rule of derivative. Then what is your guess? Will it be a linear or non-linear transformation? Is derivative linear? Derivative from polynomial to polynomial? So here, if you take that, if you take 1x x square x cube, this is a standard basis of P3. Okay, then what is this? What will be the uh, coordinate of this vector? So coordinate of this will be like a0, a1, a2. It is same as, let us write it as v. Then coordinate of v with respect to the basis b, it is same as 1x x square and x cube. Now if you consider another basis b dash 1x x square for p2, then what will be coordinate of this thing? Coordinate of d of v, this is actually d of v. What will be the coordinate?
A1, 2A2 and 3A3, sir.
Yes,
1,
1
2A2
2a2,
and
sorry, a1 2a2
3A3, sir.
So now can you write dv dash as metric multiplication with this vector? Can you write this? Sorry, this is a mistake. This should be, it is a great mistake. It should be actually the coefficient a0, a1, a2, a3. Okay. Then can you transform this to this by some matrix multiplication? Can you do that? If you can do, then D should be linear. And if you fail, then D will not be a linear transformation. Can you do that? Let us check. So this dv of B dash, you can write it as here
I guess we
a0,
can write it as
a1,
that, sir.
a2, a3. Now you can write it as 0, 1, 0, 0 because first here coefficient of a1 remain. So coefficient of a1 is 1. So here it will be 1. Now the second row, it is 2 and 0. And the third row, it will be 0, 0, 0 and 3. Right? So you are able to write it
Yes.
as some matrix with V. Okay. Therefore, D is a linear transformation. If you can write it as some linear, some multiplication with some matrix, then it will be linear. I am using that thing again. Instead of writing in this way, though it seems hard to write with this multiplication, but eventually it will be much easier to check. Okay, you can see that this can be write as some matrix multiplication, then this will be automatically linear transformation. So consider a reverse, consider the converse part, that is given the polynomial p3, if you integrate you will get a polynomial p4. So consider the integration map, I, which maps p3 to p4. This is actually integration. question is I linear or not? So what will be your answer? So let us check how I behaves. I of, let us not write I because I always seems as identity matrix. So instead of I, let us write as T. Okay. Now the question is T linear or not? So T of A0 plus A1 plus A2 x square plus A3 x cube. What will be the integration of this? This is same as A0 plus A1 x square, sorry, A0x plus A1 x square by 2 plus A2 x cube by 3 plus A3 x to the power 4 by 4. Now you can, there is a slight issue. What is the issue? Because we know integration, for integration there will be some constant, integral constant. Okay, but instead of defining C here, let us remove C. Now what will be your answer? Is T linear or not? Again, you can check that. Actually, you can write this is V and this is actually W. So the basis V with respect to the usual basis, that is this B. With respect to this basis, it is A0, A1, A2, A3. And this TV or W, it is same as with respect to the basis B. Here we need another thing, that is B dash is that basis 1 x x square x cube x to the power 4. Okay. So with respect to this basis, this is same as 0 because there is no constant term. There will be 0. Then A0 times x. Then A1 by 2 times x square. And the last entry will be A3 by 4 times x cube. A3 by 4, sorry, there will be another 2 entry, A2 by 2, A2 by 3, and A3 by 4. Okay. So can you write W as some matrix multiplication with this vector? Can you write it?
Last row would be 0, right, sir?
Hmm?
You write it in the
One.
matrix form, the last row would be 0.
There is A3 by 4. So that is what I have written. Coefficient, what will be coefficient of x to the power 4? It is A3 by 4, right?
Yes.
That is what I have written. So can you write this in terms of some matrix multiplication? This is a 5 by 1 matrix. So, and this is 4 by 1 matrix. So we need 5 by 4 matrix here. There will be 5 rows and 4 columns. What will be that thing? So first row is 0. Here you can see that first row is 0. So everything will be 0, 0 and 0, 0. Okay?
4 zeros.
4 zeros because there are 4 entry here. We need to multiply with those 4 entries. Now what will be the second row?
1 0 0 0. So
Yes. The coefficient of A0 is 1 here. So 1 and everything is 0. Similarly, the second here will be half and everything is 0. 0, 0. The third entry should be 1/3, 0, 0, 0, 0, 1. Okay. So here this is actually some matrix A times V. So the answer is yes, T is linear. Okay. Let us give some definition. One important definition is what is rank? Rank of a linear transformation. We are all already familiar with rank of a matrix, or we know those things, but what is rank of a linear transformation? So given T maps P to W, linear transformation, then rank of T, this is same as rank of column space. Column space. Okay. So for this transformation, T x1 comma x2 R2 to R2, this is same as x1 comma 0, that is projection on x-axis. Then what will be the rank for this transformation? What is the rank of T?
1, sir.
Yes, 1. Because, sorry, rank of, not rank of column space, yes, rank of the image. Okay. Because image.
So rank of T is in this example
Yes,
1, right?
rank of image. Rank of image means because TV, rank of image is also a vector space. Okay. This TV, the image, TV, this is also a vector space. Okay. Subspace of W.
सर ये बहुत क्लियर नहीं हो रहा है.
Okay. So for this uh, linear transformation, what is TV?
TV is equal to
x1 comma 0 for all x. This is a subspace of image, subspace of this R2. Okay. Not only a subset, this is actually subspace because this is closed under addition and closed under scalar multiplication. So now, what will be rank of this image? Means rank means this dimension. Okay, sorry. What will be the dimension of this image? So what will be your answer? You can see that this x1 comma 0, this can be written as x1 times 1 0, right? So you can see that the image, this TV, it is actually generated by span of 1 comma 0. Okay. Therefore, what will be the dimension of the image? Dimension of image is TV, it is actually 1. Okay. This is actually rank of T. So rank of T is.
Excuse me, sir.
Okay. So
Is it because, excuse me, sir.
yes.
Is it because the span goes on like along a line, right, sir? Like 1, 1, 0, 2, 0, 3,
Yes.
0, 4, 0. It
Yes.
goes on and on like that.
Yes, those are in x-axis. So you can write any element as linear combination of those x-axis. That is those basis element. This basis element 1 0. Okay.
So since it creates a line, it has one dimension. So
Yes.
the rank of T is 1.
Yes. This is the motivation.
Sir, I didn't get it. Like, sorry, but here, what do you mean by dimension of image? Like, image means हमने जो like we saw earlier, image is across some line. So here, where like what is the image meaning of image?
Image means range. Okay, image means range.
Range. Okay.
Image or range are similar word.
Okay. Okay. So you are saying that whatever the transformation is doing, that is the image.
Yes.
Okay.
For example, for this transformation, everything goes to that x-axis. So image is x-axis now. Okay.
Yes, yes, yes. So
So
whatever the transformation is doing, the given transformation, that is the image.
yes,
Okay. So you are saying the dimension of the image is the rank of the transformation.
yes. Dimension of the image is the rank of the transformation.
Okay. And can you please quickly once again just tell, because I'm slowly understanding. That's why.
Okay, it is
Thank
okay.
you.
So I have taken an element from the image. Okay, image is like this because of the definition all x1 comma 0 where x1 belongs to R. So I have taken an arbitrary element from the image and you can write it as x1 time 1 0.
Yeah.
So image, this image set TV or range, this is same as this is actually generated by 1 comma 0, this element.
Mm-hmm.
Hence rank will be 1. Consider another example. So this was the example we have already considered. Okay, so here if you consider this example, here the image is like this. Okay, so you cannot see what will be the real thing, that is it uh, is it completing the whole R3 or it is lying on some subspace,
So,
for example
so
some
you
plane or not.
so you found that A matrix, is that the base, is that the span for uh,
Yes, you are right. So
okay.
instead of doing any those things, you can just directly check that what will be the rank of this matrix.
Okay.
So rank of this matrix will give the rank of the image or rank of the range.
Okay.
Okay,
Thank you. Yeah.
great. So here you can see the rank of what will be rank of this matrix. This is, suppose this is A. What is rank of A? So let us reduce A. If you apply some operations, apply row operation. Okay, it is 1 minus 1 2, and now this is actually, if you multiply, if you subtract, this will be 0, 2 times the first row, this is 3, and this is minus 5, right? And here it is adding with first row, this will give 0, then it is minus 2, and this is 4.
-2 and 4.
And similarly, if you again apply, uh, instead of doing anything from here, you can directly say that rank of A is 3. Okay, because if you reduce further, there will be two different entries. There will be some 1 0 here if you reduce it further. So rank of A will be 3. Hence rank of this transformation is 3. Okay, therefore rank of T, this is 3. Here if you consider this example, what will be the rank? What will be the rank of this derivative? What will be your answer? Look at this matrix. Is it 4? What will be the rank of this matrix?
3
Yes, because there are 3
non-zero rows or 3.
non-zero
Yeah.
columns or 3 non-zero rows, whatever you say. So rank of D, it is actually 3. What will be rank of this integration? What will be rank of this integration? This matrix, this linear transformation. Here you can see there are 4 non-zero column, non-zero row, or 4 non-zero column, whatever you see. So rank of T will be, because it is already reduced, you need to just change the rows. That is, you have to take the first row to fifth. It will give the row echelon form. From here, you can see that rank of T will be 4. Right? So this
One
is rank.
question, sir.
Yes.
Like, let's take a 3 cross 3 matrix, sir. And let's say its rank is 3.
Okay.
Will the row vector span the whole 3-dimensional space as
Yes.
the column vector, sir?
Yes. As column vector, it may not
Only
be
because
true,
that we control,
but
sir.
yes, yes. For 3 cross 3 matrix, it will be true, but in general, for any 4 cross 3 matrix, this may not be true, because here you can see. But the thing is that row rank and column rank are always same. Okay.
Then
This
it says that I mean, if we take vectors of row or vectors of column, it will span the whole space, right, sir?
whole R3 for
Space
R3.
or subspace. Yeah.
But for example, if let us consider this 1 0 0 0 0 1 0 0 0. Now row, what does the row span? Span of row. So let
Spans R also.
so denote v1 as 1 0 0, v2 as 0 0 1. What will be span of this v1 bit? This will look like an arbitrary element will look like, here it will be a, here it will be 0, and here it will be b. Right? A, b are any real number from the linear combination of this. Now, if you take the column, this column and this column, okay, so denote it by w1, denote it by w2. Then what will be span of w1, w2?
A and B, sir. A
It will
comma B comma 0.
a comma b comma 0, where a b belongs to R. So does this mean row space and column space are same? Does this mean that? So the answer is no. No.
How is it, sir?
So here you can see
Oh,
that
yeah. Yes,
0
sir.
is,
Yeah.
so those are not same, but up to isomorphism those are actually same. I will define what is the meaning of isomorphism. Okay. So row space and column space may not be same. Actually, those are two different vector spaces. Row space is actually row space are 1/3 matrix. This is actually 1/3 matrix, but here it is 3/1 matrix. Okay, there is the first difference. But row and column rank will be same. This is the fact. You can see that dimension of this vector space is also 2, and dimension of this vector space is also 2. So row and column space will be of the same. Will be same. Row space is not same as column space. So let us define null space. Again, consider the linear transformation from V to W. Okay, what will be null space of T? So null space, suppose
Given matrix A,
n be the null space. We are denoting null space by n. Then null space is all the vector V such that T of V is same as 0. So the question is null space of T, is it a subspace of the V? What will be your guess? So let us check. So what do we need to check? We need to check if null space is closed under those linear combination. Okay, so check take any v1 comma v2 from the null space. Now we need to see that their linear combination cv1 plus v2, is it belongs to nt or not? This is the thing we need to check. So what is your guess? So is it?
we can multiply matrix A on both sides and we can arrive at a conclusion that gives
Okay,
0.
it's right.
So it's closed.
If we apply t on this linear combination, then you can see by the definition of linear combination, this is same as ctv1 plus tv2 by the definition of linear transformation. But v1 v2 belongs to null space, so t of v1 as well as t of v2, those are actually 0 by the definition, right? Then this is actually c times 0, this is also 0, hence this is same as 0. Therefore answer is yes, the combination belongs to null space. Null space is defined in that way, that is, take all the vector which goes to 0. Okay, take all the vector which maps to the 0 vector, right? So instead of defining this, you can say null space actually inverse image of 0 vector. Is it okay?
Image. So like A inverse matrix. Is it like A inverse matrix?
I'm saying the inverse
I mean,
image of 0 because T may not be a matrix. For matrix, it will be right. It will be the inverse matrix. But I'm not saying that T is any linear transformation. So
could be any function. Yeah.
yes, as a function, it we are saying inverse of. Actually, we should not use the notation. As a function, this is T inverse function.
Okay.
Sir, can you please help understand this? Not very clear.
Instead of this thing,
Yeah.
just think as inverse of 0. What will be the preimage of 0? Okay, those preimage are
Can you please tell, like, so every vector is being transformed to a zero vector?
yes. Those
Okay.
vectors will be are in null space. Okay.
Okay, so this transform is such that all vectors are getting mapped transformed to zero.
Yes.
Okay. Hmm.
So let us see an example. Then it will be easier. Consider again that transformation R2 to R2 to R2, T of x1 x2. This is same as x1 comma 0. Then the question is what will be null space? So which vectors goes to 0? What is your guess?
X1 equal to 0. So.
X1 equal to 0. That is, you can see immediately that if we see the projection, all vector which lies on this y-axis, this goes to actually 0 under the projection, right? Okay, let us verify this. Suppose x1 x2 belongs to null space. Let this belongs to null space. Then apply t. This should be 0 vector by the definition of null space. But what is t x1 x2? This is same as x1 comma 0. So this should be same as 0 comma 0, right? Therefore, this will imply x1 is 0 and another will 0 equal to 0. But second will be not helpful. So what will be the element of, what will be an arbitrary element of the null space? Therefore, null space is same as the x1 should be 0 and second entry can be anything. Okay, x2 belongs to
X1.
right.
Yes, 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 sir. Yes, sir. Sorry, sir.
So I am saying that this 0 comma y, any element on the y-axis, this will goes to 0. From the picture, you can see that, and here is the verification.
Sir, x2 also should not go to 0. x2.
Means
Sir, this second line which you have, therefore x1 comma 0.
yes,
So we are saying transformation of x1 comma x2 is going to x1 comma 0.
yes. This is the definition of the transformation. This is actually given.
Okay, okay.
Okay.
So because this is going to 0, 0, so this means so sir equal to 0, 0 because we want to how can we equate the transform to 0, 0? So
Okay.
does this mean that
Okay, right. So I am trying to see which element goes to 0. So I have taken some element from the null space.
yeah.
Now we are applying the transformation.
Okay, okay. I got it. I got it. So you are saying that if for
If
whenever
this
we
goes to 0 0, then
yeah,
this should be satisfied.
correct, correct. So you're saying whenever we do this kind of finding the null space, then we have to find the trans. How can we take the transform in such a way that it maps to 0, 0,
0.
right?
Yes, yes.
Okay, okay. Thank you.
Okay. So this is the null space, and you can see that null space actually subspace of this R2, right? This y-axis, everything is closed. If you take any two element from the y-axis, their sum will be in the y-axis. And if you stretch any element, this will also lie on the y-axis. So this is null space. This is actually closed under addition and scalar multiplication. Here we have verified that fact. Okay.
So, excuse me, sir.
Yes.
My question is rather basic, actually, but I need to get answered, sir.
Yes, sir.
What's the difference between span and vector space, sir, and subspace? Sir?
What is the difference between span?
Span, vector space, and subspace. Sir.
Okay,
I
span.
mean, they all denote the space that it spans, right, sir?
Yes, yes.
So, what's the
So
difference between?
yes, actually, spans mean what you have thought is right. That is, any subspace can be thought as spanning of some basis element. Okay. So here, for example, in this case, you can see that y-axis. This thing actually spanned by this 0 comma 1, this vector. So any subspace will
Yes,
arise
okay.
from span of some vectors. Okay. What you have thought is true. That is, any subspace arises from spanning set. Arises from
Okay, sir.
spanning set.
But
Yes.
one more thing, sir. But span doesn't have to be closed under multiplication and addition, right, sir?
Yes.
For
Here.
something to be spanned,
Yes. Yes. Here,
it
for
doesn't have to
example,
be closed under multiplication.
yes. For example, span of 0, 1, comma 1, 0. Those thing. It is actually R2. But you can see that those two elements, this spanning set, this is actually not even closed under addition. If you add those two things, you will get 1 1, and 1 1 does not belongs to
Yes,
this.
sir.
Okay, so span is not closed under. So this spanning set is not a vector space. But if you span, then you are getting the whole R2. That is, if you take the linear combination of those two elements, you are getting the whole thing, whole R. Is it
Okay,
clear?
sir.
Okay, great. So this is what nullity, and from here, so let us check some example. So what will be nullity of this transformation? What will be null space of this transformation? What is your guess? So
The
again,
rank of
yes, null space may not be rank. Let us check this example again. So that was the previous question. So T is defined by integration. So let a0 plus a1 a1 x plus a2 x square plus a3 x cube. This belongs to null space of this transformation. Then by definition, so suppose this is actually v, then t of v should be 0, right? But what is the integration? What integration do? It is a0x plus a1 x square by 2, a2 x cube by 3 plus a3 x to the power 4 by 4, right? This is 0. What is 0 in polynomial? 0 in polynomial means 0 everything. That is 0 plus 0x plus 0x square plus 0x. So what is when a polynomial is identically 0? When will it be true? So this is,
the vectors are independent.
yes. Then those a0, a1, a2, a3, everything should be, every coefficient should be 0. That is a0 is 0, a1 by 2 is 0. Every coefficient should be 0.
That means the vectors are linearly independent, right?
Yes, yes. So, yes, that is what the meaning of 1x, x square, x cube, or those things are linearly independent. So this means a0, a1, a2, a3, everything's are 0. Okay. So therefore, what is the null space of the T? What is the null space of this T? From here, you can see that
R4, sir.
what will be the null space? Yes.
R4, sir. Because they are independent
No.
and
You have taken an element from the null space, and this forces that those coefficients a0, a1, a2, a3, everything should be 0. Okay.
yes,
So null space should be like this: a0. So everything are 0. So 0 plus 0x plus a2. A2 means 0, x square plus a3. A3 means again 0. This is the null space. So this is actually identically 0. Except 0, there is nothing. Okay. Is it clear?
Here we can, uh, here we can plug in any value for x, right, sir? I mean,
If
if we write this, I mean, if we write this in matrix form, we can
yes,
plug in any value for x. So any
so
combination will be 0, right, sir?
no, this is not right. For example, if you integrate x, what will be integration of x? Is it 0?
No, sir.
It is actually x square by 2. Okay. So from this you can see that null space only contains 0, because every some vector which contain in the null space, this actually forced that those a0, a1, a2, a3, everything should be 0. So only vectors which contain in null space a0, a1, a2, a3 should be 0. That is what I have written, and this implies null space of T will be 0. Okay.
Okay, sir.
So this was the example, integration example. Here you can check that uh, what is the null space of this, that is, what is null space of uh, what will be the null space of this matrix. What will be the solution? What will be the solution space here?
A not equal to 0, A1 equal to 0, A2 equal to 0, and A3 equal to
A3
0.
equal to 0. Everything should be 0. Okay. That is, I am saying what will be the solution for this ax equal to 0. What will be the solution for this?
So we have only one column vector that gives us the 0 vector, right, sir? One such combination of all the vectors in matrix.
Uh, this is actually 5 by 4 matrix, and you have seen that row rank is 5, the rank is 4. Okay, and there is n is, here it is n is 4. So the answer will be, solution, there will be only n minus the rank. What is rank? Rank is 4 here, and n is also 4. So there is only 0 in linearly independent solution. That is, this is actually full rank matrix, right? This is actually full rank matrix. So except 0, there is no solution. This will imply, this this will imply x is 0, because it is full rank matrix. Okay. So instead of what?
Excuse me, sir. Can you elaborate on what is full rank matrix?
Full rank means
Uh,
it is actually
I
n
have
by,
vague idea.
yes, it is m by n matrix, and full ranks means the rank will be either m or n. Okay,
Okay, sir.
the maximum possible rank. This is the meaning of full rank.
So max of m comma n, right, sir?
Yes, yes. So this is the number of, that is number linearly independent solution, number of linearly independent solution, and you can see there will be no solution except 0. Okay.
Uh, uh, 1 second, sir. In 5 cross 4, the max maximum value is 5, right, sir?
No, no, maximum is not possible. The minimum between m and n.
Oh, minimum. Oh, okay.
Sorry for that confusion. Yes, because you cannot expect there will be 5 independent vector, right?
Yes, sir. Yes, sir.
Yes. So now we will give another definition. Nullity. Nullity is defined by dimension of null space. Okay. Nullity is same as dimension of null space. So here, what will be the nullity for this transformation? What will be NT? What will be nullity? Nullity of this transformation. So here the null space is 0. Only 0 vector is in the null space. So what will be the rank of dimension of this null space?
1, sir.
What will be basis for this 0? What will be basis for 0 vector space? You know that 0 vector space, the basis of 0 vector space is empty. There is nothing because 0 is linearly dependent. Okay. So what is now? What will be your answer? What will be nullity of T?
2, sir.
Say
Yes, it is 0 because there is no linearly independent element in this vector space. Okay. So here, for this question, what will be nullity of T? What will be nullity? Here the null space is generated by this vector 0, 1. So basis of this null space is 0, 1. Then what will be nullity? What will be dimension of this space?
A real number, sir.
Dimension.
one dimension.
Yes,
1 cross
it will be one dimensional. So nullity is 1 because every vector will look like 0, x2, and this is same as linear combination of this vector. So there is only one element, one linearly independent element in the null space. So for this question, for uh, this question, what will be nullity? Nullity of this transformation. That is transformation by this matrix. What will be nullity of this? You have
0,
already,
sir.
yes, you have already seen there is nothing. So nullity of this T, it is actually 0. Okay. Now what will be nullity of this transformation? Here rank is 3. What will be nullity of this transformation T? Here D is the transformation defined by derivative. D maps in this way. D of
0, sir.
0, is it 0? If you solve for Ax equal to 0, this is A. Okay. If you solve for Ax equal to 0, then what will be the number of linearly independent solution? Now here it is 3 by 4 matrix and the rank is 3. Rank of the matrix is 3. Rank of A is 3. So what will be the number of solutions? number of linearly independent solutions?
One only.
One solution can be there, right?
Hmm.
The solution is actually explicitly, you can see the null space. Here the null space, you can see explicitly, it will be only this A0, where A0 belongs to real number. That is the constant thing, right? Because if you if you do derivative of this constant thing, this will goes to 0. So this is actually one dimensional thing, because this is generated by 1, span of 1.
Sir, will you be sharing this video?
Yes, I'll share this video.
Sir, by when? Sorry, can you please tell by when can you share?
Yes. I'll share it by today. Okay.
Yeah. Thank you. Yeah. Some things I'm not very clear, so I want to listen again once.
Yes.
Thank you.
I'm saying that here you can see that rank of this matrix, this is actually 3, but there are 4 column, right?
Yeah.
So what will be the number of linearly independent solution? It will be number of column 4 minus rank of the matrix 3. So number of linearly independent solution for this matrix is 1.
Mhm.
The solution will be this 1 0 0 0. This is the linearly independent solution.
Sir, when there is a 0 row, we take the pivots and we uh, take the non-pivots as the independent variables, right?
Yes.
So
Here
here,
you can see that pivot elements are 1 2 3,
yes.
right?
Hmm.
That is what we are taking. So 0 in the pivots.
Okay.
Here the second column, third column and fourth column are 0. This will automatically imply that first column should be 0 also, right? Because what are the conditions? That is, A1 should be 0, 2A2 should be 0, 3A3 should be 0. What does this mean? This will automatically mean A1 should be 0, A2 should be 0, and A3 should be 0, right?
Yeah. To make it
To make it 0. So
0. Yeah.
you can see from this that A0 can be anything. You can take A0 to be anything.
Mhm.
So actually 1 0 0 0, this will be the basis for null space. This will be the basis. You can choose one anything, because there is no constant for this first element, right?
Mhm.
Because the first column is 0 0 0.
Yes,
Because
first
of that,
column 0 0
we
0.
don't have constraint on that, right?
Yes, we don't have constant on A0. So here you can see that nullity of this thing is 1. Okay. So from all of this example, if you add rank and nullity, here rank is 3, nullity is 1. You can see that dimension of P3, what will be dimension of P3? It will be 4 dimensional, because it is spanned by 1, x square, x cube. And those are linearly independent vectors, right? And if you add rank and nullity, this is also 4. Similarly, here also it is 4 dimensional. The domain is 4 dimensional. If you add rank and nullity, This is also 4. Here also, here you can see that rank is 1 and nullity is also 1. We have checked that what is the nullity? Nullity is also 1. And dimension of the domain, this is also 2. So this is not a coincidence. This is actually a theorem. Okay. This theorem is called rank nullity theorem. This says if T is a linear transformation from V to W, then rank of T plus nullity of T, this is dimension of the domain, dimension of V. It is true for any linear transformation, not only for those particular linear transformations. How do you prove? Actually, you can prove by this way. So, suppose I am giving the sketch. Suppose V1 up to Vn, those are in the null space. Vk, let us write as Vk. Those are in the null space. Those are the span, those basis for null space. Okay, not nullity, null space. And now you can extend this Vk plus, you can extend those Vk plus 1 up to Vn. This is basis for range space, not Vk plus 1 up to Vn. So it will be not basis for range space. I am trying to say V1 up to Vk. Now extend V1 up to Vk to Vk plus 1 up to Vn such that this is the basis for the vector space, the domain. Now you can prove that those Vk plus 1 up to Vn, those the image of those things, this will generate the whole W. Okay. The difference, that is the dimension of the V, if you remove the dimension of the null space, because null space goes to 0. Okay, this is not giving anything, so we can remove the null space, and rest of the thing, this will generate W. And not only this generates W, this tvk plus 1 up to tvn, this will be linearly independent. This is the fact, right? This will be linearly independent. This will be actually range set. The span of this will be range. If you use this fact, you will get that rank and nullity, this gives the whole dimension of the V. Okay, because if you take combination of these things, T Ci C1 V1 up to Ck Vk and Ck Vk plus 1 up to Cn Vn, if you take a combination and apply T, first C1 V1 up to Ck Vk, these things goes to 0 by the definition. Okay, because those are from null space NT. So other things will give the range space. This is not doing anything. Those n elements, those are Cn Tvn. So you can see that the whole range space is spanning by those Vk plus 1 up to Vn. Now you can easily see that these elements are actually linearly independent. Okay, this tvk1 up to tvn, those are linearly independent. So those are actually basis for the range space. And the theorem says using this you can construct the whole basis of V. Okay, so let us consider an example, then it will be clearer. Here t is given by this way, uh, t from R2 to R2 given by txy equal to x plus 2y, comma 2x plus y. The question is, what will be null space, what will be range space, and what will be the rank and nullity. So answer, so suppose x comma y, this belongs to null space. Okay, then t of xy, this should be 0, but this will imply x plus 2y and 2x plus y both are 0. That is x plus 2y equal to 0 and 2x plus y equal to 0. Okay, you can see this is nothing but 1 2 2 1. This is the matrix here, right? Times xy, this is actually 0 0. Then what is the meaning of this? You can see a, if you do row operation, this will become 1 2, now 0 minus 3, and again if you do row operation, this will be 0 1, right? So what will be the solution for this equation? What will be the solution for this equation? Therefore, yes, x equal to 0, y equal to 0, because this will imply this equal to 0 0, and this is same as saying x equal to 0 and y equal to 0, right? Because those are already in the pivot. Okay, so there is no non-pivot things which will be independent, which we can choose independently, right? There is no non-pivot row. So that is why we are getting x and y are 0 0. So the null space of this transformation nt, this is 0 0 space. Hence nullity of this space will be 0, because 0 is generated by the empty set, span of empty set, right? Now what will be range of this t? By rank nullity theorem, what will be dimension of the range? What will be rank? What will be rank of this space?
0 plus 2, sir.
Yes, it is dimension of the domain, dimension of R2 minus nullity of t. So 2 minus 0, 2. So range space is 2. Therefore, RT will be the whole R2, right? R2 will be this whole R2. Okay. Another way to see this, you can see that this matrix, what will be rank of this matrix? Rank
2.
is 2. Okay, therefore range will be everything. Actually, this theorem is equivalent, rank nullity theorem is equivalent to this thing, this observation, that is number of linearly independent solution which correspond to null space, and number of, if it is, so let us write it explicitly. So A is m cross n matrix. Now if you consider Ax equal to 0, then number of linearly independent solution, this correspond to null space, number of linearly independent entry in range, that is if you take it range, this correspond to range of the transformation or image of the transformation, and this n, this will correspond to dimension of the domain. Okay, T is mapped from V to W and T is defined by A. Then you can see that dimension V, this should be addition of those two things, and this is what we are getting, that is this n, this is same as rank. If you subtract rank from n, this will give number of linearly independent solution. Okay, that is n is same as rank of the matrix A plus number of linearly independent solution, right? So this is same as saying this thing, dimension is same as rank plus nullity. Okay,
Is it because of the fact that we can plug in any values for the components in x vector
what?
for v0? I mean, if let's say let's take 3 cross 3 matrix,
Yes,
and
3
the
4,
rank is 2,
rank is 2.
so we can so one row will be completely, one row or one column will be completely 0, right?
If you
So
reduce
that can,
one row and one column, if you reduce, then one column, one row will be completely 0, row reduction.
yes, sir. So
Yes,
we can plug in any value for that variable, that corresponding variable, right? So in x, ax equal to 0.
yes, you can plug in any anything for that corresponding to that row. That is, the solution will consist those things, where the third row will be anything. You can choose this third entry, this will be anything, and because this is non-pivot entry. Okay, yes,
So null space is the space which is spanned by that vector x set.
yes, yes.
Okay.
Hmm. And this null space correspond to that solution Ax equal to 0. Okay,
Okay, sir.
great. So here is, so the meaning of the, so what is the reason for introducing matrix? This is the main reason. That is, you can you can see any linear transformation For example, here the linear transformation is from polynomial to polynomial. Okay, this is completely different from those R2 or R3, R4, because here the entries are polynomial things. But though this is different, if you take the coordinate of those element, coordinate of these things here, if you take coordinate of this thing, this completely, now this thing is completely now m by n matrix. This transformation is completely defined by this m by n matrix. So this is true for any finite dimensional vector space. Any linear transformation, you can write it as some m by n matrix. And the interesting thing is that rank of this m by n matrix, this is actually rank of the range. Okay, rank of the linear transformation. And number of linearly
Range or
independent.
domain?
Yes.
Range or domain, sir? Yeah,
Range,
it would be
range.
range.
It
Oh,
will be,
okay, sir. Okay.
because suppose there are three linearly independent rows, linearly independent columns, then linear combination of those three things, that is a0 times this, a1 times this, and a2 times this will be the range. This will be the linear basis for the range. Okay,
Yes, sir.
if you write in this way. This is the main interesting thing. Oh, the thing is that matrix representation of transformations. Okay, any linear transformation can be represented by a matrix. We have already done these things. That is, if we consider this x1 comma x2, t maps from r2 to r2 by the same thing, txy, suppose this goes to x plus 3y, then x plus y. You can write it, because what will be xy coordinate of xy with respect to this standard basis? This is same as x comma y. Okay, so now if you see t of xy with respect to standard basis, t of xy with respect to that standard basis, this is same as x plus 3y plus comma x plus y, and it can be written as 1311 xy. So any linear transformation can be written as some matrix multiplication. Okay, this linear transformation, for this linear transformation you are getting a matrix multiplication, 2 by 2 matrix from R2 to R2. On the coordinates, it is any, you are taking any vector, so you are taking any matrix, 2 by 1 matrix here, and you are getting another 2 by 1 matrix here by this multiplication. So the whole linear transformation, it is now just a matrix multiplication. Okay, so any linear transformation can be represented by some matrix multiplication. How do we check? We'll see where the basis element are going. Okay, so let us try an question, an example.
So can you please scroll up just one thing I wanted to say? Yeah, here. So you wrote that R2 to R2 transformation goes to X. Uh, sorry, what is that, sir? Sir, 2 minus 1?
Which thing?
The purple
No, it is 2, 1. Sorry.
2 comma 1. Okay, okay. So 2 comma 1 is the, sorry, what does that notation mean? Like just
R2, you can thought R2 as 2 cross 1 matrix. That is, an entry will look like A comma B. This will
okay,
be multiplied with A. Okay. For
okay,
example, here this xy goes to A times this xy. Okay.
okay. So uh, X, which is a 2 cross 1 matrix, goes to a multiplication of another matrix into 2 cross 1. Okay,
It is yes, and A is 2 cross 2 matrix. This matrix.
okay, got it. Got yeah. Thank you.
Welcome. So question. So suppose T be the linear transformation from. Let us consider another thing. Suppose this is from P3 to R. Not this. Suppose this is actually R3 to R2. Okay. So T is defined by this way: T x1, x2, x3. This is actually 2x1 plus x2, x1 plus x3. Now the question is, what will be linear? What will be the matrix representation of T? What will be the matrix representation?
2, 1, and 0, sir. The
Okay.
first two.
Answer. So what will be an basis for R3? It is the standard basis E1, E2, E3. And basis for R2, it is actually another different thing, 10,01. This thing. Right. Now we'll see where those E1, E2, E3 goes. So what is TE1? TE100. What will be that? By definition, what is TE1? It is 2, 1. So it can be. So let us give it the name F1, and this is F2. So this is actually 2F1 plus F2.
Sir, sorry to disturb you. Like, what is E1, E2, E3?
It is the standard entry. E1 means 100,
Okay.
010, and this is 001.
Okay.
So now, can you tell what will be TE2? What will be TE2?
T2 is T010.
T010.
Comma 0, sir.
Yes, E2 means here
2, comma 0, sir.
2, 0. It will be x2 means here it will be 1 and there is no x2 in the second end.
Yeah, 1, comma 0, sir. So
1, 0. So you can write it as, what is the 1, 0? What is the meaning of 1, 0? It is actually f1, right?
base vector. Yes, sir.
F1 and 0 times f2. So let us write another thing, T3, T0, 0, 1. Then what will be T3?
0, comma 1, sir.
Yes, there is no x3, there is x3, so 0, 1. And what is the meaning of 0, 1? It is actually
So F1 plus 0 f2.
0 f1 plus f2, right?
Like f2 is what, sir?
0, 1.
f2 is 0 1, this element.
Oh,
So now, therefore,
oh yeah. Okay, sir.
representation of t with respect to those bases. So this is actually b, and this is actually b dash. B and b dash. This is actually transpose of those things, transpose of those entries 2 1, 1 0, and 0 1. Okay, so 2 1, 1 0, 0 1, transpose of this entry. So the representation will be 2 1, 1 0, 0 1. Is it okay?
Why do we transpose it?
Why do we need to do this transpose? Because if you write in the column form again, okay, if you write it as column form, then you can see that x1, x2, x3, sorry, this x1, x1, x2, x3, this goes to 2x1 plus x2, then x1 plus x3. That's t. And this is same as saying
N cross 1.
what will be the entries? 2 1 0, 1 0 1, right?
Yes, sir.
So this is the reason behind the transpose.
Sir, one question. What is this notation T uh, basis B, and above that you have written basis B dash?
Yes, this is the notation for this representation. What will be representation of this t with respect to some given basis? Those bases are already given. Okay, b and b dash are already given. Now the question is to find matrix representation of t with respect to those bases.
Sir,
Actually, the,
basis we have assumed, right? These values be the basis we have assumed for our convenience, right?
yes, for our convenience, we are assuming, but it can be anything according to the given.
Okay.
Okay.
Yeah. I but then sorry, I didn't understand what this when we are saying what is the T B and B dash. That part I still not very
Okay.
clear.
Here B is the basis for R2,
Correct.
R3, the
Yes.
domain. And
Yes.
B dash is another ordered basis for the range,
Yes.
for codomain R2. So those
Mm-hmm.
are given. Now we are trying to write T as a matrix. But T is not a matrix. We can write it as some matrix multiplication.
So does this notation mean that B is the domain and B dash is the range?
Yes, B is the domain and B dash is the basis for range.
Okay, and so that is so this transformation, writing this transformation as a matrix where B is the domain and B dash is the range. We This is
Yes,
how we write it. Like
yes.
that's
How yes, this is how we write.
okay.
And the interesting thing is that since T is linear, the whole linear transformation, it is only depend on how it it acts on the basis element E1, E2, E3. Okay. The whole linear transformation completely dependent on how it acts on the basis elements E1, E2, E3.
Mhm.
And we can create the whole transformation by this. Because E1, E2, E3, it will give the representation this, right? Instead of doing this, we'll do this. Okay, this is the way how do we find matrix representation. We'll given a basis E1, E2, E3, and we need to check where those E1 goes, which combination E1 goes, which combination E2 goes, and which combination E3 goes. We'll put those combination here and we'll take transpose. And this will give this. Is it okay up to this?
Yeah.
Okay. Then we'll continue again from this thing. If you have any question, feel free to ask. Otherwise, you may leave.
Sir, can you publish your email address once again, please?
Okay, I publish it. Okay. Thank you.
Okay. Thank you.
Thank
Bye.
you.